In this video, we will explore the history of the atom and how its structure has developed. It wasn't until the early 1800s, during John Dalton's work, that the ideas of atoms and particles were linked to the evidence produced experimentally. John Dalton suggested atoms were the building blocks of nature, and he believed atoms could not be split. Based on his experimental work, he suggested that atoms were very small spheres which were hard. He also suggested that during chemical reactions, atoms are able to rearrange themselves and come together with other atoms in different ways. These ideas are still useful today. They help people to understand elements and compounds by visualising them, and his models are still being used to describe the particle arrangements in solids, liquids and gases. Electrons were discovered in the late 1800s by a scientist called J.J. Thomson. The electron is a tiny particle with a negative charge. An electron's mass is 2,000 times smaller than the mass of the lightest atom. Thomson discovered the electron when experimenting with gases at low pressure. He applied high voltages to the gases, producing beams of particles. These particles were attracted to a positive charge, meaning they must have had a negative charge present. The source of the negative charges were electrons. These electrons must have been supplied by the atoms of gases in the tube. This meant that John Dalton's atomic structure was incorrect and led Thomson to produce his own theory. His theory became known as the plum pudding model. He knew that atoms had to contain a positive area, as he knew atoms had no overall charge, but electrons were negative. He believed that there was a cloud of positive charge in which the electrons were embedded, giving the appearance of a plum pudding. About 10 years later, an experiment with radioactive particles by Geiger and Marsden produced evidence for the existence of a nucleus. In their experiment, they fired alpha particles at a piece of gold foil. If the plum pudding model of the atom was correct, the particle should have passed straight through the gold atoms of the foil. The results of the experiment showed that some of the particles passed through the foil and emerged at different angles, and some of the particles were deflected back by the foil. Using these results, Rutherford suggested that the plum pudding model was incorrect. He used the results to suggest that the positive charge of the atom must be concentrated in one small area at the centre of the atom. This area is called the nucleus, and the nucleus contained dense positively charged particles called protons, and the electrons must orbit the positive nucleus. The next development came from the suggestion of electron shells. Bohr studied results from experiments involving atoms being heated. He noted that the specific amounts of energy were given out in the form of light when the atoms were heated. This led him to believe that electrons must be orbiting by a set distance from the nucleus, and that electrons were fixed in shells, with each shell having a specific energy. He suggested that the energy is given out when electrons that have been excited to a higher shell fall back down to a lower shell. The final development in the structure of the atom was the neutron. Scientists believe that the nucleus contained two types of subatomic particles, with one being a proton. Scientists knew that the second particle had to have no charge, as the overall charge on an atom is neutral. For this reason, neutrons were difficult to detect experimentally. Eventually, in 1932, an experiment by James Chadwick proved the existence of neutrons. Next, we are going to look at the subatomic particles and what is meant by ions and isotopes. Protons, neutrons and electrons are called subatomic particles. The proton is positively charged, with a relative charge of +1 and a relative mass of 1. Neutrons have no charge and so have a relative charge of 0, but a relative mass of 1. The nucleus has an overall positive charge. Electrons are negatively charged subatomic particles with a relative charge of -1. Every atom contains equal numbers of protons and electrons, so this means the atoms have no overall charge. This also means you can use the number of protons in an atom to work out the number of electrons. Electrons are tiny and so their relative mass is also tiny. Their mass is so small it is often stated as 0. When the number of protons does not equal the number of electrons, it is no longer called an atom. You now have an ion. An ion is an atom or a group of atoms which have become charged. Ions are formed when an atom gains or loses electrons, often during bonding. If an atom gains electrons, a negative ion is formed, and if an atom loses electrons, a positive ion is formed. If an atom loses one electron, such as an atom of sodium, it has one more proton than electron. The ion formed will have a charge of 1+. When we talk about charges, the number always comes in front of the sign. If an atom gains 1 electron, the ion has a charge of 1-. The rule continues for gaining or losing 2 or more electrons. When representing ions, we use the chemical symbol for the elements and show the charge. For example, the 3- ion of phosphorus is represented by P3-. For each element on the periodic table, you will notice 2 numbers. The number below the symbol is the atomic number. The number above the symbol is the mass number. The atomic number is also called the proton number, as it represents the number of protons in each atom of the element. It is the number of protons which defines an element. For example, all atoms of magnesium have 12 protons. Because atoms are neutral, we know that the number of protons is equal to the number of electrons. This means that the atomic number for an atom must also equal the number of electrons. However, if you have an ion, the number of electrons changes. The periodic table is arranged in increasing atomic number. The mass number shows the relative mass of an atom, which is actually the relative mass of the nucleus. This means the mass number tells us the number of protons and neutrons. You can take the atomic number away from the mass number to work out the number of neutrons in the nucleus. Now, given a periodic table, you should be able to work out the number of protons, electrons and neutrons in any element. For instance, find the number of protons, electrons and neutrons in an atom of aluminium. The atomic number is 13, and so the number of protons is 13 as well. This also means that the number of electrons is 13. The mass number is 27, so the number of neutrons is 27 minus 13, which equals 14. If you were asked for a 3+ ion of aluminium, the number of electrons would be 10. As we have already discussed, the number of protons in an atom is used to define the element. This is because atoms with the same atomic numbers are the same element. Atoms with the same element but with different numbers of neutrons are called isotopes. This means all the isotopes for an element will have the same atomic number but will have different mass numbers. An example is hydrogen. Most hydrogen atoms have a mass number of 1, meaning that they have no neutrons. However, some hydrogen atoms have a mass number of 2, with 1 neutron, or a mass number of 3, with 2 neutrons. Some isotopes are more stable than others. The addition of extra neutrons may make the nucleus unstable, and the atom may become radioactive. Some atoms may have different densities. For example, the isotope of hydrogen with a mass number of 2 is called heavy hydrogen. This means the physical properties of the isotopes may change. However, the chemical properties are the same for all isotopes of the same element. This is because chemical properties are determined by electrons. This means all the isotopes of one element react in the same way. Atoms are very, very small. A useful way of writing the number of atoms is using standard form. This works for really small or large numbers. The radius of an atom is approximately 0.1 nanometers or 1 × 10 to the minus 10 meters. The nucleus of an atom is approximately 1 × 10 to the minus 14 meters, so this shows that most of an atom is space.